In this video, I'm going to cover a topic in chemistry called the mole. We have three objectives for this video. First, we'll talk about atoms and chemical reactions, what role atoms and molecules play in reactions. Next, we'll talk about that thing called the mole and what it has to do with how many atoms we're reacting at one time. For instance, a lot of reactions, we don't just take one of two different types of reactions that we can see here in the middle. We take large numbers of atoms and react them together. And lastly, we'll end with mole conversions, talk about how to compare numbers of moles and numbers of atoms. So first, let's talk about atoms in chemical reactions. What role do they play? So in chemistry, we are really studying how atoms interact with one another. For instance, in this chemical reaction on screen, if I represent this as atoms and molecules, I can see that if I take two atoms of silver and react it with one molecule of copper 2 chloride, I'll create a new product. Silver chloride, two molecules of it here, and one atom of copper right here. Now, the problem here is that atoms are incredibly small. As a chemist, I could not pick up these atoms and smush them together. So, how do we fix that? Well, the problem we already talked about, we can't pick up atoms or molecules because they're tiny and they don't weigh a lot. But since atoms are small, we as chemists, instead of dealing with individual atoms, we use a standard number every time we perform a reaction. So instead of counting things atom by atom, we count things as groups of atoms. That's where a mole comes in. Like I mentioned, in chemical reactions, we need to react specific amounts or ratios of atoms or molecules together. In the reaction below, we take two atoms of silver plus one molecule of copper 2 chloride, making two molecules of silver chloride and one atom of copper. Because we can't pick up individual atoms and molecules, instead we keep the same ratios, but we use many atoms or molecules as once. So instead of two atoms of silver, we use two piles of atoms that are very large amounts of atoms. And instead of one molecule of copper 2 chloride, we use many molecules of copper 2 chloride. But the ratios stay the same. For every one silver atom, or excuse me, for every two silver atoms, we need one molecule of copper 2 chloride. And this is where the mole comes in. That countable amount of atoms or molecules, when we plan our reactions, if I were to try to take one mole of like a copper block, I am defining a mole as a certain countable amount of atoms. And that mole is equal to this number of atoms. When we say we have one mole of something, we're saying we have this many atoms. But we can use this in scientific notation down here at the bottom. One mole is equal to 6.02 times 10 to the 23 atoms. That is what a mole is. And this number is known as Avogadro's number for the scientist who, I don't want to say discovered it, but really created this number through experimentation. Now, we use countable groups in life. If we have two of something, we might say we have a pair. If we have 12 of something, as in eggs, we might say we have a dozen of that thing. You could also have a dozen donuts, a dozen bagels, doesn't really matter. A dozen is just 12 things. 20 of something we refer to as a score. 144 of anything we refer to as a gross. And a mole is the same. 6.02 times 10 to the 23 of anything is a mole. You could have a mole of playing cards. You could have a mole of eggs. A mole is just 6.02 times 10 to the 23 of something that you can count. So for instance, if I take three different atoms, or three different types of atom, hydrogen, copper, and oxygen, one mole of any of these atoms is always going to be 6.02 times 10 to the 23 of those atoms. And this is true for molecules too. If you're just counting them, it doesn't matter what type you have, the mole is always the same amount. So finally, let's talk about what this skill looks like when we actually apply it in chemistry. So the real skill here is being able to figure out how many atoms are in a certain number of moles, or how many molecules are in a certain number of moles. And that's where dimensional analysis comes into play. If we know how many atoms of something we have, we can convert it to moles using dimensional analysis. For instance, let's say I give you 3.87 times 10 to the 24th atoms of carbon. If I want to give you that amount, I'll just pretend I give you a pile of atoms and it's that many atoms. With dimensional analysis, we'll always set up our known amount over 1 with no unit, and I'm going to multiply that by the conversion factor. 1 mole of carbon is equal to 6.02 times 10 to the 23 atoms of carbon. Remember, the numerator here and the denominator are equal in value, just different in unit. 1 mole is equal to 6.02 times 10 to the 23 atoms. What I will do then is cancel out my units that are on numerator and denominator, so atoms of carbon cancel. I will then multiply my numbers straight across. Notice that both of these are multiplied by 1, so in the numerator we have 3.87 times 10 to the 24th. In the denominator we have 6.02 times 10 to the 23. And if we were to divide those numbers, you would get 6.43, and the only unit that didn't cancel is carried over, just moles of carbon. In other words, if I hand you 3.87 times 10 to the 24th atoms of carbon, that is equal to 6.43 moles of carbon. So we can do the same thing, but instead of starting with atoms, if we know the number of moles of a substance, we can convert it to a number of atoms or molecules, as long as our units cancel. For instance, if I start with 2 moles of CH4, that's methane, I will put it over 1, just like dimensional analysis dictates. I'll then multiply it by my conversion factor, which is still 1 mole is equal to 6.02 times 10 to the 23 anything. Notice in this case, we're counting molecules because it is made up of multiple atoms. CH4 is 1 atom of carbon and 4 atoms of hydrogen, so we're dealing with molecules here. However, we set this up so moles cancel in this case. We then multiply straight across the top and straight across the bottom. And finally, we end with 1.204 times 10 to the 24th molecules CH4. So we can use dimensional analysis. All we have to do is make sure that this conversion factor, we keep 1 with mole and 6.02 times 10 to the 23 with that other quantity, be it atoms or molecules. One quick side note, if I scroll back right here, you'll notice that I abbreviated mole as MOL. That is very common when we use moles in mathematical operations. And that is our introduction to the mole.